Very good morning to all of you. Today I want to start session 2 of module 2, and module title is stress distribution in soils. Course outcome of module 2 is understanding of stress distribution and resulting settlement beneath the loaded footings on sand and clay soils. So this is the course outcome of module 2. Subject title is Applied Geotechnical Engineering and the subject code is 18 CV62 of 6 semesters in civil engineering departments. Okay. Contents. Today's session 2 contents are vertical pressure under uniformly loaded over circular area, and second content is vertical pressure due to a line loads. So means today class is to explain in details how to use the stress distribution concepts to determine vertical stress for the given loads in circular area, as well as due to line loads how to calculate sigma z, that is vertical stress. Okay, so today's concepts, so these contents are required to explain in details. Let us see Bosnick's theory and assumptions for circular footings or circular area. If the load is acting for circular area means in geotechnicals, practical examples are water tank, circular buildings, ring structures, foundations. So these are the examples of circular footings. Silos and bunkers are also used for circular footings. In these concepts, or in these type of cases, how vertical stress are calculated at a depth z. See, this is the diagrams. Here, this is the circular area of radial distance small r, and here to here this is the elemental area of dA, and here this is from here to here this is capital R, radius of circular footings, external diameters, acting at a depth z in meters, and this distance is nothing but a dr. Okay, and this is the centroidal axis. This is the centroidal axis. This is point P to calculate sigma z, that is vertical stress at a depth of z at a point P, acting at an angle theta, and this is d theta. Okay. This problem may arise in connections with the settlement studies of structures on circular foundations, such as gas line tanks, grain elevators, and storage bins, water tanks, etc. The Bosnick's equation for the vertical stress due to a point load can be extended to find the vertical stress at any point below the center of uniformly loaded circular area. Let the circular area of radius small r be loaded uniformly with Q per unit area as shown in above figures. Okay, this is okay. The vertical pressure at a point P situated at z depth on the vertical axis through the center of the area is given by del sigma z equal to 3 by 2 pi into q dA times z cube by r square plus z square to the power of 5 by 2. So for this equation, integrating over the center ring of radius r, the vertical stress is given by del sigma z equal to 3 by 2 pi into summation of q dA into z cube by r square plus z square to the power of 5 by 2 is nothing but a, after simplified, 3 by 2 pi into q times 2 pi into r dr into z cube by r square plus z square to the power of 5 by 2. So while deriving based on the integrations, 3 qr dr into z cube by r by square plus z by square whole to the power by 2. Okay. The total vertical pressure sigma z due to the entire loaded area is given by the total vertical pressure sigma z due to the entire loaded area is given by integrating between the limits r equal to 0 to r, integrating limits r equal to 0 to r. So then therefore sigma z equal to 3q z cube into integration 0 to r with respect to r dr by r square plus z square to the power of 5 by 2. Put r square plus z square equal to x square. Put r square plus z square equal to x square. Therefore from these equations, sigma z equal to 3q z cube integration 0 to r into r dr by x square to the power of 5 by 2. Here x square equal to r square plus z square. If r equal to 0, so then x square equal to z square. So therefore if x equal to z, so then r equal to capital R. So then x square equal to r square plus z square and x equal to r square plus z square. If r dr equal to x dx, so then where r equal to 0, x equal to z, then capital R becomes r. So then x becomes root of r square plus z square from above equations while substituting these concepts. Therefore sigma z equal to 3q z cube of integration z to root of r square plus z square into x dx by x square to the power of 5 by 2. So while integration, sigma z equal to 3q z cube integration z to root of r square z square into x dx divided by x raised to 5. So now here x square to the power of 5 by 2 is nothing but a x square into 5 by 2 is equal to x raised to 5. So this is based on the mathematical concept. Therefore sigma z equal to 3q z cube into, substitute the value here, x raised to minus 3 divided by minus 3 limits x to root of r square plus z square after integrations. So now simplified these equations, 3q z cube by minus 3, now substitute the limits, upper limit minus lower limits. So while substituting, so while solving the equation, now this becomes minus q z cube into 1 by root of r square plus z square minus 1 by z cube while substituting and simplifying. Therefore sigma z equal to minus q z cube times 1 by root of r square plus z square to the power of 1 by 2 into 3 minus 1 by z cube. So this is, I am simplifying the equations. Okay. Finally this equation becomes, after simplifying this, minus q z cube 1 by root of r square plus z square to the power of 3 by 2 minus 1 by z cube. So now after simplifying these equations, so minus q times z cube by r square plus z square to the power of 3 by 2 minus minus plus, now it's become q z cube by z cube. So therefore final equations after simplifying this, sigma z equal to q times 1 minus z cube by r square plus z square to the power of 3 by 2, or it can be written as q times 1 minus 1 cube by 1 plus r by z square whole to the power of 3 by 2. Now this is equation number 1 after derivations. Sigma z for circular footing, q times 1 minus 1 cube by 1 plus r by z square whole to the power of 3 by 2. So this is the final derivation of Bosni's equation for circular footings. Therefore sigma z equal to kb into q, where kb is called Bosni's coefficient factor for uniformly distributed circular loaded area. If theta is the angle which the line joining the points makes with the other edge of the loading, then the above equation reduces to sigma z equal to q times 1 minus cos cube theta. So this is with respect to theta value. So from the above equations, now equation 3 we are getting. Now this is explanations for isobars under uniformly loaded circular area, how pressures are distributed. See this diagram. So this is the ground levels and this at a depth z. Okay, this is the footings of diameter b, and these are the uniform intensity q load setting. So while increasing the q load, stress is distributed like that, that is 0 q, 0.5 q, 0.4 q, 0.3 q, 0.1, 0.15, 0.1 q. Means if the depth is increased, stresses are decreased. Okay. From these diagrams, the pressure distribution under a uniform circular load as first presented by Jorgensen is shown in above figures. With the help of different isobars, okay, so these are the isobar lines. With the help of different isobars given in figure above, vertical pressure at various points below a circular loaded area can be conveniently calculated. Okay, so we are calculating vertical stress with diameter b at a depth b by 2. This is b by 2 depth, means we are increasing the depth. We are calculating isobar concepts from these diagrams. Okay. Next class, next topic is vertical pressure due to a line loads. So now we have calculated, means we have confirmed how to determine vertical stress for circular footings with point loads. Okay. So now if the load is acting in terms of a line loads, okay, natural clay strata, okay, line loads. Let a load uniformly distributed along a line of intensity q per unit length of a straight line of infinite extensions act on the surface of a semi-infinite elastic medium. Such a loading produces a state of plane strain, that is, the strains and stresses in all planes normal to the line of the loading are identical, and it is adequate to consider the conditions in one such plane as shown in figure below. See here, this is the inclined lines of load is acting q per unit length, and this is actual foundations. Okay, this foundation is situated away from these points. okay, this distance x, okay, and at a depth z in meters, okay, and this footing is acting at an angle theta at a depth z at a distance x, okay. So now we can calculate this radial distance equal to root of x square plus z square, this base square plus depth square, or cos theta equal to z by root of x square plus z square. Cos theta is nothing but a adjacent by hypotenuse. Same concept is here. And see here, this is one soil elemental area. Here, this is three-dimensional figures. See, these are the sigma x in horizontal directions, and this is sigma z acting in vertical direction, that is why x is sigma z, and this force is nothing but this stress is acting in third direction, that is in y, okay, sigma x, sigma y and sigma z, in three directions stresses are acting. So then how to calculate sigma z, that is vertical stress, okay, from this soil elemental area, and these points are tau x y and tau yx, means shear stress acting, okay. The vertical stress sigma z, see this is the sigma z at a depth z, sigma z, see this point sigma z, okay. The vertical stress sigma z at point P may be written in rectangular coordinate systems, may be written in rectangular coordinate system as sigma z equal to q by z into 2 by pi by 1 plus x by z square to the power of 2, okay. Sigma z equal to q by z into 2 by pi by 1 plus x by z square whole square is nothing but a q by z into kz. Here this equation is called Bosni's equation for line loads. From these equations, sigma z is nothing but a vertical stress at a depth z in kilonewton per meter square, and q is a uniformly distributed loads per unit length, and z is the depth of the foundations in meters, and x is the distance from the foundation to the required points in meters, and this that is already given explains, that is depth in meter. So then while substituting the value, we are calculating sigma z at a depth z with respect to x distance, we are calculating in kilonewton per meter square. This is the final equations, and if the point A is situated vertically below the line load at a depth x, we have x equal to 0, and hence the vertical stress is then be given by sigma z equal to 2 by pi into q by z. So if the load is acting at the direct point, okay. So this is the explanations to calculate sigma z for line loads, okay. So these are the references are made to cover this session 2 with different textbooks, with the different IS codes, with the different journals to finish session 2, okay. Thank you one and all. Next class I will be continue.